This
inductor we had
conference
already
will
learned.
now be
Today
recorded.
we'll be discussing what happens if we apply AC signal to a pure capacitor. So we have so far learned in a purely resistive circuit, if you apply AC voltages, what happens, that we have already seen. We have seen what happens if we apply AC voltages to a pure inductor. Pure inductor means always inductor carries some resistance, but pure inductor means in a circuit there is no resistance associated with inductor. So similarly, today we will be learning what happens to the current in the circuit, or what is the current and voltage relationship if we apply AC voltage to a capacitor. Okay, this is our topic for discussion today, and if possible we'll take up few numerical examples. Let me share my presentation to you. See, today we'll be learning what happens to current in the circuit if we apply an AC voltage to a pure capacitor. As I said, pure capacitor means no resistance associated with a capacitor. Okay, so when we connect such a capacitor in a circuit, that circuit will be called as purely capacitive circuit, or purely capacitive circuit if we use this kind of capacitor. Okay, all right. So before we go to AC circuit, I'll just give you a simple overview, a short overview, what happens to DC current if we wish to charge a capacitor with DC power supply. Let me give you the circuit diagram. This is a circuit diagram. We have a capacitor. Here, this is not a purely capacitive circuit when I am charging a capacitor with a DC power supply. This is DC power supply. This is having the voltage. Power supply has the voltage Vs. And this is a capacitor, as you can see from here. And the capacitor across, the voltage across the capacitor can be measured by voltmeter. So that can be done. And as soon as we switch this on, there will be current flowing through the circuit. Okay, in case of DC, there is no change in the direction of the voltage, so there will be no change in the direction in the current in the circuit also. So what happens during this process, the positive charges will be accumulated, as you can see from here. If I just give a name A plate and B plate, and capacitor, will be always, capacitor means we'll be thinking of kind of parallel plate capacitor having two plates A and B like this. Okay, and sometime this can be an air capacitor, sometime there will be some dielectric materials inside it to increase the capacity to hold the charge. So that we have already learned in our second chapter. Okay, so in this case, you look what happens. The charges will be piled up in these two plates. Positive charges, suppose in this case will be piled up or stored in the plate A, and the negative charges will be stored in the plate B. So when there is charge, when there are charges accumulated in one plate, positive charges and negative charges on the other plate, so you can think that there are two charges nearby. So there will be obviously a potential difference across this or voltage across this. Okay, we can say this as VC, voltage across capacitor. Okay, so as the number of charges are accumulated, suppose this capacitor has capacitance C, it can hold some 20 microfarad charge. Okay, microfarad. Okay, uh, so this is the capacitance, and it can hold suppose some okay, I'll just take arbitrary number. So it is a capacitor which can hold some q coulomb charge. Okay, capital Q coulomb charge. So look what happens by connecting with the DC source. We are just charging this capacitor, so it will be charged bit by bit. Bit by bit means one charge will go, positive charge will go and accumulate at A. Corresponding negative charge also will be accumulated at B. Bit by bit it will be charged. At a, like all of a sudden it will not be charged by the whole capacity. Okay, it will be charged bit by bit. And when this happens, this voltage also changes. Voltage across this, it will increase as your charge accumulated on the plates increases. This also increases. And when after a time, maybe some hour or something like that, according to the capacity of the charge to hold the charges, capacity of the capacitor to hold charges. So when this capacitor gets fully charged, what happens? This increases. See, I'll tell you what is fully charged means. Fully charged means suppose it has. See, this is your CS capacitance. Okay, capacitance of the capacitor, and see when this capacitor gets fully charged, the voltage across this will be same as the supply voltage, that is Vs. That is Vs. Okay, so this is the expression for the maximum charge. Okay, which will be accumulated in this capacitor. And when it is fully charged, that time this Vc will be Vs. That means what? The potential across this will be exactly equal to the battery voltage. Okay, and as you know, if there is no potential difference, so if there is a, if this is Vs and also this is also Vs, so there is no potential difference across, like potential difference. Okay, from this point, suppose this is some point P, this is Q, this is R, and this is S. If there is potential difference, suppose between P and Q, this has to be actually low potential, low, and your P has to be high potential, at high potential, and R will be again lower than Q, and at S your potential has to be again lower than R. So then only there will be a flow of current. What I mean to say is that you have to have potential difference to have flow of charges, potential difference. But when the capacitor is fully charged, in case of DC source, like when we charge the capacitor by a DC source, there will be no potential difference after the capacitor gets fully charged. If there is no potential difference, then there will be no flow of current or charges in the circuit. So immediately after this capacitor getting fully charged, the current in the circuit will be zero immediately. Okay, so this is what happens. So now this capacitor is fully charged. Now if you use the capacitor to get some power from that, if you use this capacitor, now fully charged capacitor, for some use, suppose you are charging your mobile and then using the mobile. So if you just connect a battery, a bulb or something like that, so then what will happen? The current will flow from this capacitor itself, and it will glow. Okay, it will glow. So this is how charging happens. And after charging, when you use this in a circuit, this capacitor will discharge, and by that it will send a current in the circuit. Anyway, so you can see that you cannot get uninterrupted current or flow of charge in case of DC charging. That means if you apply DC power to a capacitor, after the capacitor is getting fully charged, the current in the circuit will be immediately zero. Okay, that means capacitor blocks DC current. So this is the outcome from this discussion. Okay, so whenever in any electrical circuit you need to block DC current, you need to use capacitor. We'll be see when we'll be seeing the rectifier circuit, etc. That time we'll be discussing in 14th chapter, 14th, I think 14th chapter, we'll be discussing again when we'll be discussing rectifier circuit, full wave, half wave rectifier. We'll be again seeing that this capacitor will be used to block the DC current. Okay, all right. So this is what we know for DC. Now we'll just go to the main discussion here. If we apply AC power to a pure capacitor, what happens to the current? So as you have seen, in case of DC, there is always a constant voltage which is obtained from the power supply. But in this case, the voltage is varying like this. So if I say this is Vt at any time, this varies as Vm sine omega t. This is the sinusoidal voltage. Okay, sinusoidal voltage, or the voltage varies as a sine curve like this, like this. Okay, this voltage varies like this. So in this case, this is the maximum voltage. This is called the peak voltage. This is called peak voltage or amplitude of the voltage, Vm. And you can see at any instant these are the values. At any time the values are like this. It is increasing up to maximum, and then it is decreasing again, goes to zero. And in the negative side also it is symmetric. You'll find this is minus Vm, this is actually plus Vm. Okay, like that it will be varying and reaching to maximum in the opposite direction, and again it will be decreasing to zero. So this is how the voltage is varying. So what happens in this case, in this case current will never become zero. Obviously this capacitor also will give some resistance. We'll see that some resistance to the current flow, but it will not stop the current in the circuit completely. Why? Because you look here, the voltage itself is changing its polarity. So you have a capacitor. C, capacitor having capacitance C. So see, in this first positive half cycle, this is half cycle, another half cycle is this one. So this is called positive half cycle of the signal or voltage, positive half cycle, and this is called negative half cycle of the signal. So during this positive half cycle of the signal, suppose I have capacitor plates A and B, and this positive half cycle, this guy will be charged with positive charge. Okay, I mean to say, in the positive half cycle, the capacitor will be charged, and in the other half cycle, it will be discharged. Uh, okay, so we'll be discussing this actually not in the other half cycle. So if I just break into quarter of the wave, I'll just remove this. I'll just redraw it. So we have to make it quarter, not half. Actually, in a single half cycle, it will be charging and discharging also, like this. Suppose, okay. So if I just break into four, like this, okay. So this is one quarter, another quarter is this one. So again, if I break, this is third quarter, this is fourth quarter. Okay, so as a whole, it will be the full cycle. Okay, this is T. So this part will be T by 4. This will be T by up to this. It will be T by half, and then again this will be 3T by 2, and this will be, sorry, 3 2 by 4, and this will be here T. All right. So you can break into four quarters. So look, this is a part of this half positive half cycle. During this time, the capacitor will be charged. During this quarter, the capacitor will be discharged again in the negative side. So it will be changing its polarity in this half cycle. So this will be negatively charged, and this will be positively charged. Okay, and the current direction itself will change, and this will be, so it will be charged negative polarity with this part, and it will be discharged in the fourth quarter. So this is how it will be charging and discharging because the voltage, supply voltage itself is changing its magnitude as well as its direction because it is AC. So you can understand that in this case there is no way to block the AC current. So AC current is not completely blocked or not completely stopped in the circuit. So current never becomes zero. In this case, current never becomes zero in the circuit, in the AC case, because it capacitor gets repeatedly charged and discharged because of that. Okay. All right. So let us now learn this fact analytically with some equations and mathematical formulations. Let us do something related to that. So suppose, as we have already taken, this voltage is varying like this, Vm sine omega t. Okay, omega is the frequency of the AC signal. Omega, yes, and Vm is the amplitude, as I told already. Okay, this gives you, this is actually instantaneous voltage, and this is your amplitude of the voltage. And let us say at any instant, at any instant t, the charge accumulated in this capacitor is Q. So charge is Q. Okay. charge in the capacitor is Q. Okay. So if I say charge is Q, then there will be obviously some voltage developed across this capacitor. So that voltage is this one. So this is V at any instant. Okay, Vt is equal to Q by C. Okay, this is what we know from our second chapter, because capacitor voltage, capacitance voltage and charge, they are interrelated to each other. We know Q is equal to C into V. So this is what we know from our second chapter discussion. And from there I can write what is the voltage across the capacitor at any instant t if there is some charge accumulated in the capacitor. Okay, this is what we can write. Q by C is equal to V. Okay, so far no problem. So now look what we have to find out. We have to find out the current. Okay, so before that we will write what is Vt. So this Vt actually here, this V is actually the instantaneous voltage across this capacitor, which is nothing but having the variation of this. Okay, so at any instant the voltage across this capacitor will be this Vt only. Okay, Vm sin omega t. So what we have got here is, see, I can just write what is Q from here. From this formula I can write what is Q. So once I get the expression for Q, Q means charge at any instant of time, this is Vt, so which can further be written as Vm sine of omega t. Okay, this is what can be written. Okay, this is the charge at any instant in the capacitor. So what we are just going to do today in this, not only today, in this chapter, we need to know what is the current in the circuit and what is the relationship with the voltage, supply voltage Vt. Okay, that is what we need to know. So if we want to know what is the current in the circuit, from here we can find out at any instant we can find out the current. So if I write the current is I, a function of time, then I can write dq dt. We know already from the definition of the current. Obviously we sometimes take this as limit dt tending to 0 or something like that. Okay, so we just leave it now. Okay, so dq dt, I is dq dt. So we can just take a derivative for this equation 1, suppose this is equation 2. So if we just take derivative, then I can write dq dt is equal to, see, this Vm and C are constant, I'll keep as it is. Only thing is this one is varying with time and we are taking derivative with respect to time, so it will be omega cos of omega t. We can just rewrite this as I is equal to, so I write Vm into omega c cos of omega t. Look, you know, this left hand side, so this is dimensionless quantity, as I said is last class also, in the last class. So this is dimensionless quantity. Dimensionless quantity. But in the left hand side you look, you have the dimension of current. So obviously right hand side also has to be having dimension of current. Okay, so look, this thing I know, if I just compare with my resistive circuit, if I compare this current voltage equation with resistive circuit, we know for resistive circuit, so I am writing circuit abbreviated as CKT, this part. So in resistive circuit we know current is equal to voltage, amplitude of the voltage by R. R is the resistance in the circuit. Okay, so this is how we can write. So if we just compare these two, look, this two, this is in case of pure capacitive circuit, this is pure resistive circuit. So if we compare this two, then I can write something like this: Vm divided by 1 by omega into C. Okay, I can write that into cos of omega t. All right, so I'll just clean the upper portion and then write it again. So what I have got here is I t is equal to Vm by 1 by omega c into cos of omega t. So if I compare these two, then I can say that R is C equivalent to 1 by omega c, or in other way also 1 by omega c is equivalent to R. That means this will have dimension of current, okay, dimension of current, where this has dimension of voltage and this will be having obviously dimension of resistance. So this 1 by omega c, this is having a dimension of resistance in this purely capacitive circuit. So 1 by omega c. 1 by omega c is called capacitive reactance. Okay. So 1 by omega c, this is denoted by xc. xc. So this you can see that this one, this is actually equivalent to resistance. So this is called capacitive reactance. Capacitive reactance. Capacitive reactance, and it has unit ohm, similar to resistance. Okay. And one interesting thing you can see that now from this equation we can easily explain why AC does not block, does not AC signal or AC current does not get blocked by capacitor, whereas DC is blocked by capacitor. Look, in this case we'll take this term capacitive reactance. So this is inversely proportional to omega. Omega means angular frequency. This can be written as 2 pi into linear frequency f. If I just say this f is linear frequency of oscillation. Okay, if I put it here, look what happens. This is 2 pi f into c. So what does this mean? This means your capacitive reactance, which is acting as a resistance, okay, that is inversely proportional to frequency, inversely proportional to the value of capacitance also. Okay, now look, if my frequency of oscillation of any signal is much larger, okay, much larger, then if this increases, then what happens? So increases this frequency, increases frequency of the oscillation of the circuit increases, then your xc decreases. That means this capacitive reactance act as a resistance to the current flow in the circuit. In case of AC circuit, it offers a resistance which is depending on the frequency. If your frequency increases, then your real resistance or capacitive reactance decreases. And also if you increase the capacitor, like increase the value of the capacitor, value of the capacitance I should say, value of the capacitance, then also this resistance offered by the capacitor to the circuit or to the flow of resistance against the flow of resistance will be decreasing. So look now, I have got I t is equal to Im cos of omega t, okay, where Im is equal to Vm by 1 by omega c, where omega c is called capacitive reactance. Capacitive reactance. We have learnt already what is called inductive reactance, and this capacitive reactance is actually, this is 1 by 2 pi f into c, so inversely proportional to frequency. If we increase the frequency, the resistance decreases in the capacitive circuit, purely capacitive circuit. Now see, in case of DC current, okay, for DC current, what is the frequency? Frequency is 0. So if the frequency is 0, look, this capacitive reactance or the resistance in the purely capacitive circuit, so if this is 0, so it will be almost infinity. So this will be almost infinity. That means if capacitor offers almost infinite resistance to the AC signal or AC current, but whereas in case of AC you have non-zero value of this frequency, non-zero value, sometime it will be kilohertz, sometime it will be megahertz. So these are very huge values of frequencies, and when frequency increases, the capacitive reactance immediately decreases. Okay, that means in case of AC, if your frequency of oscillation is large, then your capacitance is going to be very small or can be neglected. That's why we say, that's why we say AC is not blocked by a capacitor. Okay, AC is not blocked, whereas DC is blocked because frequency is 0. That means it will, the capacitor will offer almost infinite resistance to the flow of electric current. Okay, I hope you have understood why DC is blocked by a capacitor and why the AC is not blocked. Now I'll show you the variation of this capacitive reactance with the frequency. As you can see, so this we know x, this is xc, x suffix c, which is inversely proportional to the frequency. Okay, so the capacitive reactance here xc, and this is frequency, look like this. Okay, hyperbola. Okay, so as you can see from here, your frequency, when frequency is almost 0, see it has infinite resistance almost. This is the case for DC signal. And when you increase the frequency, look, the capacitive reactance decreases, and at highest frequency it is almost negligible or nearly equal to 0. So that's why AC signals, because they have frequency of oscillations, in those cases the signal or the current will not be blocked by a capacitor. Okay, I hope it is clear to you. Now see, what we have got is that the current in the circuit, in the purely capacitive circuit, is varying as this cos of omega t. This we have got, where your Im is Vm by 1 by omega c. All right. So look, this thing, this cos omega t. See, our voltage was V of t is equal to Vm sin omega t. Vm sin omega t. If I want to write in terms of sin omega t, this current I can write it I of t is equal to Im sin omega t plus pi by 2. This will give you cos of omega t. So now I'll just do one thing. I'll just keep these two side by side and see another agenda we had to see the phase relationship between current and voltage. So in this case, voltage is Vm sin omega t, and what we have got, the current is, this is I is equal to Im sin omega t plus pi by 2. Okay, I'll just write it again. It is going beyond the margin. I'll just write it little left side. So what we can see is that the phase angle for current is greater than the phase angle for voltage. And we have seen what is the difference in the phase is pi by 2. What is the difference in phase? That is pi by 2. And in this case, as you know, we need to know which one is lagging and which one is leading. See, in this case, the current is ahead of voltage by 90 degree or pi by 2 radian. Okay, current is ahead. So what we have to say here is that the current is leading. So here what is happening? Current is leading in the capacitive circuit, purely capacitive circuit. Current leads, okay, and voltage lags, okay, voltage lags. And when you say current leads, then you have to say by how much angle, phase angle. So we have to say here that the current is leading, current is leading the voltage by pi by 2 radian. This is what we have to say. Okay, and see here we have the Phasor diagram in this figure. You look here, Phasor diagram. Why do we need Phasor diagram in studying AC circuits or AC signals or whatever related to AC? This is needed for knowing the phase relationship just by seeing the circuit itself. Seeing, sorry, seeing the diagram itself. Okay, seeing the diagram itself. So the Phasor diagram actually we had discussed already in the previous two classes. Phasor diagram actually a diagram which has two rotating vector. One represents current, another represents the voltage, and these rotating vectors are rotating in the anticlockwise direction with the same frequency as this signal has or the current has. So by properly drawing those rotating vector, we can denote both the instantaneous and the amplitude of the current and voltage. So in this case, see this figure A. Here, this blue is giving you the voltage phasor. This is called voltage phasor, voltage phasor, generally written with capital V. Okay, voltage phasor. And this gray curve, look, this one is giving you current phasor. These are rotating vectors. Phasor means rotating vector, rotating with equal frequency in the anti-clockwise direction. So current phasor. Okay, here it is current phasor. Now look, you have to see what is the phase angle between this current and voltage you have got from analytical method. So in the analytical method, we have seen that the current will be ahead and or current will be leading and voltage will be lagging. So in this, look, in this figure, see, the voltage is lagging and current is leading because they are rotating in the anti-clockwise direction. So who is ahead? The current phasor is ahead. And what is the angle between current phasor and voltage phasor? That must be pi by 2 or 90 degree. Okay. Look, this curve, this angle, this is actually 90-degree angle. Okay, between current phasor and voltage phasor. Okay. So, and similar again, the same thing, that the projection, vertical projection will give you the instantaneous voltage. Okay. Or for the current, it will give you the instantaneous current. Okay. And the length of the rotating vector will give you the magnitude of the signal. So we have learned here that there is phase difference pi by 2 between voltage and current. Between voltage and current, there is a phase difference pi by 2. In the inductor case also, we have seen that the voltage difference between current and voltage was pi by 2, but in that case, current lags in this case. Okay, current was lagging. Okay, and in this case, the voltage is lagging, current is leading. In case of inductor, there was 90-degree phase difference between current and voltage, but that time the current was lagging the lagging behind the voltage. But in this case, current is leading by 90 degree. Okay, 90 degree or pi by 2 radian. Okay, so the curve B we had already discussed many times. So it is actually rotating vector can produce any sinusoidal voltage. This is another expression for that. Okay. So I hope you have understood the phasor diagram as well. So if you are asked to find out or write down the phasor diagram, draw the phasor diagram, then exactly you have to draw this. In case of this part, if you draw, then it is all right. So this is the phasor diagram for current and voltage for a capacitive circuit, purely capacitive circuit. When AC signal Vm or AC power AC voltage Vm sin omega t is applied. Okay. All right. So now we will go to the important part. In case of inductor, we have seen that inductor does not draw any power. Okay, that means there is no joule heating loss. Okay, here the circuit, there will be no K. So in this case also, we will try to see whether there is joule heating, and due to that there is a power loss in the purely capacitive circuit or not. So we have, see, we can find out instantaneous power. Sorry. Instantaneous power. You yourself can tell me. Power, P means we know. P is equal to VI, that we know. So we can write P power is voltage into current. So voltage Vt. So this is instantaneous It. Okay. So if you write Vt, Vm sin omega t, and what we have got this? This we have got Im cos of omega t, or Im you can just again bring this thing omega c by v omega c. Okay, you can write that also. All right. So what we can do is we can take a average power. The instantaneous power does not mean anything physically. If you want to know, about the joule heating loss, you have to get average power supply, power dissipated. So average power dissipated, let us see. Average power dissipated will be time average of this instantaneous power. This will give you average power, okay? But this is at full cycle or complete cycle. Complete cycle. Okay, so let us take average for this, average of this instantaneous power. What will be getting actually? This P average is equal to, suppose this is written as capital P, will be Vm Im Im. If I just take 2, like if I divide with 2, then it will be sine omega t cos omega t with 2 here multiplied cos of omega t. So it will give you Vm Im divided by 2 into sine of 2 omega t. Okay, I'll just write it above. So average power, which is obtained from the instantaneous power, taking average itself. So you'll get Vm sine of m, sorry, Vm Im by 2. This you have to find out the average of this. Okay. So we have seen in full cycle or complete cycle, this average gives you 0. In the previous class also we had discussed that. I'm not going to repeat that now here, but we can use the result that the sign any odd number, odd or even number, other than squares, anything you take other than squares or half, further high power. If you take any sine omega t, sine 2 omega t, 3 omega t, etc. If you take time average of that will give you 0. So what is the average power dissipated in the capacitive circuit, purely capacitive circuit? That is also 0. Okay, that is also 0 here. So average power dissipated in the capacitive circuit is 0. Okay, that means what? Capacitor does not lose any power due to his heat, due to joule heating. due to joule heating. And the current flowing in this circuit, this kind of circuit is called wattless current. This I had already discussed, but this we will be discussing in detail what is called wattless current. Okay, this is called wattless current. The current in the capacitor, because it does not waste any or does not have any joule heating loss. Okay, so why this power is not being consumed by the capacitor, that is explained very nicely in your book. I'll just briefly tell you how to analyze that there is no power dissipated. Similar to inductor, we have some explanation for this. Look, as I said, you can divide a full cycle of the signal. Look here, the full cycle of the signal is, see, this is your signal voltage kind of this VC goes like this. So you can just this curve is VC. So this goes a complete sine curve. Now the current, look, this thick one is current, and this one is VC. Okay, and look, in this case capacitors are getting charged. So charge also varies sinusoidally because your supply voltage is varying sinusoidally. The current through the circuit also will be oscillating. Then the charge which is getting accumulated and discharged again, that also oscillates as sine curve. Okay, now we can take up first quarter of the cycle 0 to 1. In this case, you look, the current is flowing in the when current is flowing in the circuit from, because the positive half cycle, because of positive half cycle, this will actually, there will be current flowing in this direction. And you look, this A and B, these plates will be charged with certain charges. So in this case, suppose the positive half cycle will charge the plate A with the positive charges and the plate B by negative charges. And there will be obviously voltage VC across this, or VAB I can say, which can be written as VC again. So this potential drop across these charges will be increasing. And look, in the first quarter of the cycle, you look, this is the current, this is the first quarter. What happens, it is actually it has started from maximum, then the current will be 0, or you can just take the voltage is 0 in the beginning, then when charge gets accumulated, then it will be maximum here. Okay, so the charge will be maximum, that time the VC is this. And again, then what happens in the region 0 to 1 to 2, that means in the second quarter of the cycle, what happens, so the current will be still flowing A to B, and you can see that the charges are less over here. So what happens, when the polarity, see here, the polarity of VC is still positive, but the current is negative over here. In the previous case, so in this quarter, first quarter, both current, voltage and charges, they are positive. So power is also positive. Okay, for the first quarter, power is positive. That means what? Positive power means capacitor is absorbing power from the absorbing power from the AC supply. Okay, so AC supply battery. All right, when the power is positive. So see, during this half cycle, 0 to 1, sorry, quarter cycle, this in this case, see, this is the current, this is positive, the voltage also positive. So instantaneous as well as average power will be positive over here. And in the other quarter, you look 1 to 2. In this case, see, charge accumulated is positive, but it is decreasing now. VC also decreases, and also the current also decreases. So you look here in this region, current and voltage are actually both are sorry, voltage is positive, whereas your current is negative. Here this is current. Okay, so current and voltage, if they are in opposite polarity, so the power, you look here, this one, this power is negative. So in one quarter of the cycle, as I was saying, it is getting charged. In another quarter, it is getting discharged. Okay, it is getting discharged, and it is reversing its polarity. It will be charging in the negative direction again. And charging means, see, in this third quarter, in the current and voltage, this is the current, and voltage also has a sinusoidal variation. So both will be negative in this third quarter. So current, this is current negative, and look, charges also it is going to be negative. That means the polarity of the capacitor, the charge capacitor will be changing. So A will be negative, B will be having positive because of this current is going to be negative, sorry, positive, and voltage is still negative. That's why it is negative again. So anyway, so current is changing its polarity. According to that, this A, B plates also will be changing their polarity. All right, so you look here, P is positive. Again, in the fourth quarter, you look, the current is totally positive here, and voltage is negative. Okay, so voltage is negative and current is positive. That means the power also will be negative, negative power. So that is here. So in a complete cycle, it will be once charged, and in the next quarter cycle, it will be discharged. Again, it will be charged in another quarter cycle, and in the fourth quarter cycle, it will be again discharged. Okay, capacitor will be absorbing power and releasing here. When the power is negative, power is restored or returned to the supply again by the capacitor. Again, in the third quarter, it will be absorbing power from the circuit, power supply. And in the fourth quarter of this cycle, power is negative. That means the power is returned to the circuit again. Power is returned to the supply battery, to the supply. Okay, so this is how, because of this charging and discharging, once it is charging, another quarter it is discharging. Because of this, it is absorbing power and again returning back to the supply. That's why it is not like, as a whole, if you take the average of all these powers, like just sum up all of them and then divide with 4, then you will get 0 values for the power dissipation. Okay, this is how, just like your inductor, in case of inductor also, the power was absorbed and released in the next quarter cycle. Okay. So this is how you can analyze why inductor or capacitor, they do not consume power or lose power in the form of joule heating. Okay. So with this we'll stop our discussion here today. We'll meet again on Wednesday. So I'll stop it here. Bye for today. See you again on Wednesday.